Hello, everyone. Welcome back to the GOCC. So today we have Leonie from the Max Planck Institute in Leipzig speaking about hyperplane arrangements, reciprocal linear spaces, and logarithmic discriminants and beyond. Before we get started, let's just recall our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that, Leonie, feel free to take it away.
Yeah, thank you so much for having me. And I definitely don't have all the answers also in this talk today. Um, but yeah, so this talk will be about a project joined with Andreas Kretschmer and Simon Thelen about 2024, 2025. And I've talked about this several times, but I've never really kind of given an in-depth talk that gave me an opportunity to also talk about the related combinatorics that are mostly still unexplored. So I would like to take the opportunity here to say what we did, but also point into many open directions. And the main combinatorial object that we will be looking at today, we will, yes, are affine hyperplane arrangements. By this, I just mean an ordinary collection of hyperplanes in the usually C to the D, or sometimes the real field R to the D. And we have always n many hyperplanes, and the ambient dimension is always D. So in the picture here, we're looking at 5 lines in the real plane, given by 5 affine linear equations. And yeah, if you're familiar with only homogeneous hyperplane arrangements, so where there is no constant term, I will in a second tell you how to translate between these two worlds. But yeah, so this is a very nice structure, and the way we encode this is usually by giving the coefficient matrix of of these linear equations, where we kind of single out the first row, which are the constant terms, and then the remaining of the matrix are the linear terms. And so I will be following somewhat the choices we made in the paper, which means that L will always be this rectangular matrix. This has n columns, one column for each linear form. The first row is the constant term, and then the other d rows are the coefficients of x1 to xd. The caveat is that in the paper we made the unfortunate choice to have n+1 hyperplanes everywhere. This was reasonable at the start and turned out to be a bit annoying at the end, but we kept it in. So for this talk, I made the effort to reduce all the numbers n+1 to n. So do not, like, if something feels off, I maybe has forgotten to go one step back from n+1 to n. Um, but yeah, today we will have n hyperplanes. If you try to kind of cross-read the paper, that's a warning. There we have n+1. And yeah, these two matrices, so the full matrix A and with the row B stacked on top, and just the matrix A, these two will kind of guide us through the talk and their combinatorics and their matroids. Um, but first, some more notation. The rank of an arrangement is just the rank of this linear matrix A, which is also the same as the vector space dimension of the normal vectors of the hyperplanes. So usually it's just D. So we don't have a common direction of the hyperplanes, so that the full rank just essential is what it's called. Just means that the hyperplanes point in all directions, at least the normal vectors. But we can still have, of course, as you see here, kind of parallel lines, and they give us interesting properties. And X, the main player today, will not quite be the arrangement A, but rather its complement in usually C to the D, sometimes when we draw pictures, also R to the D. And this is an interesting variety or manifold. Um, and before we go into the rest of the title, I promised to talk about hyperplane arrangements. Check. Before we go into these discriminants and the reciprocal linear spaces, let's stay a bit in the hyperplane world and look at the interesting combinatorics that hide there. And so one fundamental invariant of an arrangement is its characteristic polynomial, which you get by summing over all sort of subarrangements, so any collections of the hyperplanes from no hyperplane to all hyperplanes, and we sum over those whose intersection is not empty, and then we sum over like the the parity of the number of planes that we took times t to the dimension of the intersection. So the highest term will always be the intersection about the empty set, which is the full ambient space. So t to the d is always the leading term. And then we have lower order terms. There is an example in the next slide. And if you know about lattice or semi-lattice theory, you can alternatively also sum over the geometric semi-lattice given by the flats. I will not say right now what flats are because we largely don't need them, but if you know matrices, you may have seen the characteristic polynomial defined in a different way, and this indeed also exists for affine hyperplane arrangements. With this in place, there's a super nice kind of connection between this sort of combinatorial counting of intersections and their size to the topology. And for one, the cohomology groups with integer coefficients of the complex hyperplane arrangement complement. There are three groups of finite rank BI. These are the Betti numbers. And the Betti numbers are precisely, let's say, up to sign and reordering the coefficients of the characteristic polynomial. So the characteristic polynomial, so this dissection gives you a nice description of the Betti numbers. And in particular, if we plug into the characteristic polynomial 1, we get the alternating sum of the Betti numbers, which is to say the Euler characteristic. The Euler characteristic of the hyperplane arrangement complement is just characteristic polynomial evaluated at 1. So sum of these coefficients. And if we instead look at real arrangement, we can also say something, namely the number of connected components of the real arrangement complement is the characteristic polynomial evaluated at -1, and then deleting the sign if it occurs, and the number of bounded components, or if you are not an essential arrangement, you have to take relatively bounded components. This is also the evaluation at 1 of the characteristic polynomial, which sort of gives you the interesting relationship that if you have a real arrangement, which you might as well also consider as a complex arrangement, then as a complex arrangement complement, its other characteristic up to sign equals the number of bounded cells in the real arrangement complement. I think that's a really, really cool connection between the real and complex world. So let's look at an example. Here we have the same arrangement as in the first slide. So we have five lines. So the sum goes over, okay, first the empty intersection is all the planes, so this gives us t squared. Then we have 5 ways to choose a line. So we have minus 5t. Remember, this minus is just alternating between the number of hyperplanes we choose. So we have minus 5t because a line is dimension 1. Then we take the intersections of all pairs of lines. So we have, out of these 10 pairs, 8 of them do intersect in a point. And the 2 parallel ones do not intersect, so we discard them. So we have a contribution of 8 of pairwise intersections. Then we take triple choices, and there are only 2 ways to choose 3 of the 5 lines that do intersect not in the empty set. It's these 3 and these 3. So we have to, in the next set, have to subtract 2 again. And then if you choose 4 or 5 of the lines, the intersection is empty, so they don't contribute. So the characteristic polynomial of this arrangement is t squared minus 5t plus 6. And so if you then want the Betti numbers, for example, 6 is, 1, the leading coefficients would be b0, which is just saying that there's one connected component. Indeed, the complex arrangement complement is connected. And then 5 would be the Betti 1, and 6 would be Betti 2. And Betti 3, Betti 4, despite the complex complement being 4-dimensional, they are 0. And now if we plug in 1 into the characteristic polynomial, we get 2, which indeed, as the picture confirms, is the number of bounded chambers. There are two triangles that are bounded. And it's also the Euler characteristic of the complex picture, which I can't picture because it's four-dimensional, but I trust the math. And if we instead plug in -1, we do get 12, which is also confirmed by the picture that there are 12 just connected components, bounded or not. And I promised to connect this to those of you who are familiar with matroids. In order to do this, we have to add one more column to the matrix L, namely just the first standard basis vector, so that sort of our matrix, which was previously just B stacked on top of A, now has one first column, and then we associate it to the arrangement and called affine matroid. And an affine is just a matroid together with one particular preferred element of the ground set. So geometrically, this would be taking the arrangement that we have and adding the hyperplane at infinity as one more n plus first hyperplane. Indeed, the equation, if you homogenize this, say, take the closure instead of CD in projective space PD, then the first basis, standard basis vector is indeed the equation of the hyperplane at infinity. And if with this notation, all of the previous things can be now stated in terms of the matroids. For example, these big matrix, so the matrix L, and this little matrix, which is just the linear terms, can be seen as the deletion and the contraction of this new element E, and the characteristic polynomial of the arrangement chi of A equals the reduced characteristic polynomial of the matroid M. And the reduced characteristic polynomial is just the characteristic polynomial divided by 1 minus t. If you're not familiar with matroids, don't worry and just take the previous definition of the characteristic polynomial for the hyperplane arrangement. But just in matrix theory, if you evaluate the characteristic polynomial or the reduced one, rather at 1, you get something called the beta invariant of the matroid. So this is sort of telling you that this Euler characteristic, the arrangement, is connected to the famous beta invariant of the matroid. And today, or at least in the paper with Andreas and Simon, we were mostly interested in the most generic possible case. So all the matrices are sort of random, which amounts to saying that these two matrices are uniform. So any collection of at most D or D plus 1 in the big matrix are linearly independent. All the minors are non-zero that can be non-zero. But yeah, all of these combinatorics can in principle be done in general, or have been done in general. It's just that part of our proofs, as we will see in a minute, do heavily depend on some like minimal amount of uniformity that we want to impose. Okay, that's for the basics of hyperplane arrangements. And now we take a step into the direction of discriminants by talking about maximum likelihood estimation in algebraic statistics. So there are sort of two applications in which this comes up. I will be here phrasing it in the terms of algebraic statistics, but it also comes up in particle physics. But I will today kind of fix this this angle here. So we pick a discrete statistical model. It's just a subset of the set of numbers r to the n, numbers or vectors in r to the n that are positive and that sum to 1. And one way to get such a statistical model is just to take an algebraic variety, which might as well be a complex variety, and then we intersect it with these reals. The task of likelihood estimation, or the maximum likelihood estimation, asks, okay, we have a sample of points u of n counts of the states 1 to n, and we ask which point in our model X explains best this data observation by which we mean we want to maximize the likelihood that this occurs, and the likelihood is just the product over xi, so the point in the model, to the ui, the count on the data. So this is the kind of very general task in statistics of maximum likelihood estimation. And one way to solve it is just to say, okay, we have a smooth manifold X, let's say a real manifold, and so we want to optimize a function on it. So we just might take the gradient of the target function, this LU, and set it to 0. So this would give you the critical equations. This will today be denoted by crit x from the parameter u. And it turns out that for almost all possible data u, this is a finite set of non-degenerate critical critical points. And the number also doesn't depend on u for general u. And this is called the maximum likelihood degree of this particular algebraic variety X. Was there something in the chat? I heard it plop.
Oh, I was raising my hand.
Hi.
Can you-
Okay, and this this maximum likelihood degree, so the number of critical points
Leonie?
for complex solutions, is turns out to be the Euler characteristic of this variety X.
I can type my question.
And this is an important invariant. Is the connection bad? Sorry, is it?
I think there's a question from Ethan that might pop up in the chat in a moment.
Can I say more about the real versus complex points happening here? I can try. So of course, the statistical point of view does only care about, I mean, for a statistical model is just a set of probability distributions, and discrete means because we have just n states, so we have a subset of r to the n, and this set delta n minus 1, the probability simplex are just n vectors, real n vectors that sum to 1 are positive. Because this is where the actual likelihood maximation takes place. So this is in this, so to speak, in the real part of the variety X. And here, for example, in the picture, I should have mentioned the picture earlier, this is the example of the binary independence model. So you have 4 states and kind of 1, 1, 1, 2, 2, 1, and 2, 2. And the question is whether this this distribution kind of is independent, so it's a product of 2 binary random variables with potentially different biases. And here, the surface you can see are the real solutions, but the variety corresponding to this would be the Segre variety, which is the P1 times P1 in P3, which is of course 1 dimension too high, but so this is rather a projection into 3 space. Or rather, it's sort of picking a chart in which you can see the vertices of a probability simplex, these 4 vertices. So for a statistics point of view, only the real solutions make sense. However, if we want to count things and we want the count to be insensitive to the data point, we need to count complex solutions. And so we take the gradient here, which gives us algebraic equations, which we want to solve over the reals, but in order to kind of get a structural understanding, we get to take the count over the complex complex solution. So all points of X, not only the real points. I guess this is the subtlety, and maybe also a caveat that the ML degree may be significantly overstating how many critical points there actually are. But it's a good first approach, and we can compute it in many cases, for example, by the result of Juniha that this is the Euler characteristic. All right, perfect. And today we're looking at the particular case of linear models, though the entire discussion is also interesting for other algebraic models from algebraic statistics. Oops. And what is a linear model? It's essentially just a linear subspace of this probability simplex or the C star to the n. And what we do is we take an arrangement of n hyperplanes, again defined by linear or affine linear functions L. And so to make it into a statistical model, or like as in the previous slide, we need to embed it into C star to the n, which is varieties that allow for this are called very affine. And so maybe I should first tell you when is this the case, and this is the case if and only if the arrangement is essential, which means that the normals point everywhere, that this matrix A on this arrangement had rank n, D, sorry. And so from now on, we will only consider really the essential arrangement, which is not really a restriction, and all our most important or interesting arrangements are either already essential, or you can easily make them essential by sort of quotienting out some linear space. And then these linear functions just give an embedding of the hyperplane arrangement complement X into C star to the n, which is just saying that our model is a affine linear subspace of C star to the n, or of C to the n, and you remove the coordinate hyperplanes. And because only the image is important for this, we might as well rescale everything to be summed to 1. This would make a statistician happy, but this is, again, not important for our discussion because it's sort of scaling invariant. And so what is the likelihood function here? Well, we have a nice parameterization by the Li. So the log likelihood function is the logarithm of the Li to the u, which you can just by the log rule get to the front. So it's u1 times the log of L1 of x plus the other terms. And the critical points are now given as the points where the gradient of this function Lu of x vanishes, which, so you may worry, okay, the logarithm is not an algebraic function, scary, but the derivative gets rid of this and introduces sort of 1 over the Li, which is a happily irrational function. So this gives you algebraic equations on X, on the hyperplane arrangement complement, because we need to invert the Li, of course. And in the case of real arrangements, these critical points have a very nice structure. Vashenko showed that the critical points correspond in a one-to-one way to the bounded chambers. So what I should really say here is that in this particular case, all critical points are in fact real. And in each of the bounded components, remember the previous example, there were these two bounded triangles, each of them hosts one critical point, exactly 1. And so in a way, you could kind of, if you wanted to do likelihood estimation, you could just pick every bounded component and look, okay, where's the critical point? This is a very nice structure. And we will later see that this implies, under mild hypothesis, a positivity result on the discriminant, but I'm getting ahead of myself. What I will not really talk about today is that these equations, also the same critical equations, also appear as the scattering equations in particle physics and biojoint scalar phi-3 theories. So there are different independent interests in these equations, and if you're interested, I could point you to some references for this. And so this definition of ML degree required you to have a general data U, and then ask, okay, that's the ML degree is the number of critical points. But what is general data, you might ask? On what happens if you move from general data to special data that maybe violates this property of ML degree equals number of critical points? So there are roughly three things that could happen. You could have two critical points that are isolated and happy, and they move towards to form a degenerate critical point. You could have that there is somehow a positive dimensional, so an infinite set of critical points. Or you may have that the critical points escapes to the boundary of the hyperplane arrangement complement, so to say, to infinity. And this is exactly what we need to avoid. So if we're outside of the condition 1, 2, 3, then we do have ML degree many critical points. And motivated by this, Rodriguez and Tang called the locus where these bad things happen, they call the data discriminant. And one of these cases, namely the going to infinity, is somehow of a different flavor, and this was studied by Sattelberg and van der Veer. And this is somehow not the same phenomenon, because it could in principle be solved by compactifying accordingly. However, the phenomenon 1 and 2 are really you have to deal with it. And this is our, say, at least ad hoc definition of a logarithmic discriminant. So we arrived at the second part of the title. The logarithmic discriminant of such a smooth algebraic variety or algebraic statistical model is the set of points U, so the data points, where the critical set is either non-reduced or infinite. And the goal of the project and the rest of the talk essentially is to understand these logarithmic discriminants for hyperplane arrangements. And nothing helps this more than connecting it to things you probably know. So let's look at 3 points on the line. This is sort of the smallest example that you could look at. And after moving the points around, you may want to fix point 0 and point 1, and then there's a third point B. This is indeed a hyperplane arrangement. It's a hyperplane arrangement on the line, so the hyperplanes are just 3 points given or defined by 3 equations, x minus 1, and x minus b. As a quick check from the previous formula, the ML degree here is 2, because, for example, the Euler characteristic of the complex plane C punctured in 3 points is 1 minus 3, which is 2. Alternatively, in the picture, you also just see there are 2 bounded segments, and so that's again 2. So for most data points U, you have 2 critical points, and if they're real, Vashenko tells us that one is in the segment 0, 1 and one in the segment 1b, at least if b is positive, if b greater than 1. And we can rearrange the critical equations, so the gradient of this LU equal to 0, to get one nice quadratic equation in X with U coefficients. And the logarithmic discriminant essentially asks us, when does this quadratic in X have a double root? So for most parameters U, it has distinct roots, 2 distinct roots. But when does it have a double root? Well, when the high school discriminant vanishes, this 4b squared minus AC, no, b squared minus 4AC. And if we evaluate the high school discriminant of the quadratic discriminant on this polynomial, we get a degree 2 polynomial in U, and this is the logarithmic discriminant of 3 points in a line. And this is kind of a funny coincidence that here again, the logarithmic discriminant gives you a quadric, a smooth quadric, for which you sort of can see that this has indeed, if this vanishes, then the U's cannot be real. And we will later see that indeed for at least positive, they cannot be positive real. And indeed for positive data points, Vashenko's theorem essentially tells us that we do not have a degenerate critical point. Before we can go into more results in the logarithmic discriminant, I should give you a more careful definition of what a discriminant is, because we also want to compute it, and so far I can't tell the computer to do it, and I would like to call the computer how to do it. And how to do it is to realize that this is something called the ramification locus of a map of smooth varieties. Sounds very scary, but it's a very intuitive thing. If you have two smooth varieties, think just manifolds, such as these surfaces, say, and you have a surjective map, then you can ask, okay, which points upstairs, so on X, are not isolated in the fiber. So the fiber just means we apply the map, go to the bottom, and then we take the preimage back again. So either you're isolated in the preimage, or you're not isolated, or which means that you're part of a positive dimensional component containing your point X, or you are isolated, but you are part of multiple points. So a point of multiplicity or a ramification point. This is what the ramification locus is. And if you want to compute it, you just take the Jacobi determinant. So we take two varieties of the same dimension. So they have the Jacobi map as a square matrix locally, and its determinant vanishing exactly tells you that you're in the ramification locus. And the branch locus is then just the image of the ramification locus. And if we apply this to the likelihood correspondence, which is just pairs u of x, where x is a critical point to parameter u, so to say, Lu, the gradient of Lu at x vanishes. This is a n-1 dimensional variety. And if we then project down to Pn-1, so to the parameter u, this is exactly the setting in which we could apply this definition, and then we get that the likelihood correspondence, which has equations, and then the determinant, which, because this is sort of, the likelihood correspondence is already the gradient, so the determinant of this gives you the Hessian matrix, or rather the determinant of the Hessian matrix, and this defines the ramification locus. So these equations in the definition, these are things that you can actually throw at a computer and ask it to compute it. So this is essentially how all the examples in this presentation and also in the paper have been computed by doing this, doing some elimination, and then obtaining the equation. And we can do some more simplifications by kind of looking further at the equations. So the gradient L of u is just this expression, so the matrix A times a diagonal matrix of the inverses of the linear forms times u. And then if you take the Hessian determinant, you get sort of a nice symmetric matrix that has A and A transpose on its sides. And if you apply the Cauchy-Binet expansion formula for determinants, you get a sum over all subsets of size d of the indices. So you get sort of an explicit formula of the expansion of the Hessian determinant. And if you observe this equation, the critical equations here, they are linear in the ui or uj. So you can just rearrange them to express u1 and up to ud in the other u's. So we can just substitute them away, and we obtain a polynomial h tilde in the remaining variables. And this, the ramification locus is then, because this is just a substitution, this is just isomorphic to the vanishing set of this particular one polynomial. So the ramification locus is an irreducible variety exactly when this polynomial is an irreducible polynomial. So this is a purely algebraic statement about one particular, be it quite complicated polynomial. But using this, we kind of got to our first result, saying that if the arrangement contains a smaller arrangement of d plus 2 hyperplanes, which is biuniform, so the all the matroids involved are uniform, then kind of this goes through. We can show algebraically that h tilde is an irreducible polynomial, and hence the ramification locus is a variety, and so the projection that logarithmic discriminant is also an irreducible variety. So at least in the case where everything is sufficiently uniform in general, we indeed have an irreducible reduced hypersurface, or let's say variety. We don't know yet that it's a hypersurface. That's unfortunately much harder. but this may make you kind of curious to say, okay, is this condition necessary, or is it maybe always irreducible? And the answer is sadly no, or interestingly no, I should say. If you pick this arrangement of three planes in space, and the way that this was chosen is the planes are sort of generic, but the first three intersect in a line and the last three intersect in a line. But other than that, there are no unexpected kind of intersection behaviors. And if you do this and then calculate the discriminant as we did before, the discriminant splits into three components. We have two quadrics, which sort of should remind you of the arrangements of points on a line, because this is, again, these are smooth quadrics. And the third component is even worse. This has codimension 2. So there's a linear subspace that also appears here. This corresponds in the ramification locus to points that are not isolated in the fiber. So they sit on a positive dimensional fiber. So for specific arrangements, things can indeed go crazy. And I would very much be interested in understanding more in detail which property of the arrangement make things stay irreducible or have a lower dimensional component. I think this is a very interesting question. And coming back to points on the line, I wanted to sort of give you sort of a complete answer here, because this is where we can just use standard intersection theory arguments to success. We can say that the ramification locus is a smooth irreducible hypersurface. This is essentially the previous result, because for points on the line, all arrangement of points are sort of uniform. And if you take the closure of this likelihood correspondence, you can obtain its class in the Chow ring, which is just the cohomology ring of the product of projective space with the line. And then, because we want to take the ramification locus, which is just the projection, the discriminant is the projection of the ramification locus. So we also need the condition that this is generically bijective, and indeed it is. And once you have this, you can just collect this coefficient from the class in the Chow ring and obtain that the logarithmic discriminant is an irreducible hypersurface of degree 2 times n minus 2. And even better, there is a almost closed formula in terms of the ordinary plane univariate discriminant. So in the first example of 3 points, this was the quadratic discriminant. And if you have n points, you have the also univariate discriminant. I see a question by Galen. Hi. We currently do not have any other specific arrangement results beyond generic arrangements, but this is indeed something that I would love to look into, and I think Bailey and friends, I don't remember your co-author, sorry, also had a look at this for graphic arrangements, and there's many things to be explored. Yeah, if you're interested, yeah, feel free to send me an email afterwards. Before I can state the main result, the statement for generic arrangements, I wanted to mention the third concept from the title. Now we have the full title assembled, namely the reciprocal linear space. And what is a reciprocal linear space? If you take the linear forms and you invert them, you take just the image of this map, which is sort of a linear map composed with the Cremona map, and then take the closure. If this sounds scary to you, you can also think of it in almost linear algebra fashion. You take a linear subspace in C to the n, and you pick all the coordinates, all the points in it that have non-zero coordinates, but where all coordinates are non-zero, you invert the coordinates, and then you take the closure. This is a reciprocal linear space. It's literally the reciprocal of a linear space. What a fitting name. And this object is super nice. It's currently my favorite variety. I'm sort of fangirling for this right now. It is a homologically nice. It is a projectively Cohen-Macaulay variety of the same dimension of the linear space, but projectivized. We have access to universal Gröbner basis of this variety. This is indexed by circuits of the matrite of the matrix L, which is to say you take linear, minimally dependent collections of columns, take the relation that gives you this this dependence, and write this as coefficients in a polynomial, and you have a universal Gröbner basis of the ideal. I think that's fantastic. And this coordinate ring of RL degenerates to the broken circuit ring, which is not on the slide, and it's combinatorially very interesting, but not so important. But I just wanted to mention that at least the degree of the variety is one other important invariant of the matrix. It's the Möbius invariant of the matrix of L, which is just evaluating the characteristic polynomial at 0. So it's sort of the Möbius invariant of in the semi-lattice of, in this case, the lattice of flats. And why did I bring this up? Why is this relevant to our story here? We take, if we take the critical equations on the hyperplane arrangement complement X, and this is a nonlinear equation because we invert X, clearly. So you may have the idea that, okay, if we just take the image of X under this coordinate-wise inversion, which is to say, the thing that we take the closure of to get the reciprocal linear space, then suddenly this becomes a linear condition. To be very precise, X is a critical point to parameter U, if and only if gamma of X, where gamma is just inverting the values of the linear functions at X, lies in the linear space that is the kernel of the matrix A transpose times the diagonal matrix of U. And I guess the image, if you will go over all X, this gives you RL, or at least the interior of RL. So the critical points correspond to a subset of the intersection of this reciprocal linear space with a linear space that depends on U, so this phi of U. And now we're interested in ramification points, so points where somehow you have a degenerate critical point, or you have multiplicity, and this corresponds in the geometric picture of intersecting RL with the linear space to linear spaces that non-transversally intersect the reciprocal linear space in its smooth locus. That's a technical addition. And this locus, this first associated hypersurface, is defined by one polynomial in the Plicker ring of the Grassmannian. So kind of the collection of all linear spaces that non-transversely intersect RL smooth locus by the Howitz form. And Bernd Stumpfels proved, basically building on this degeneration of the coordinate ring of RL to the broken circuit ring by Broadfoot and Spire. He showed that the degree of the Howitz form is again a matrix invariant, not quite as like famous or basic, but it's less a combination of coefficients of the characteristic polynomial. And equipped with this, I can finally give you the main result of our work. We take again a generic arrangement, so all the matrices that we care about are uniform, and we previously knew already that it's an irreducible variety, the discriminant. And now, equipped with this extra tool, we can also show it's indeed a hypersurface. And then there is a second discriminant that kind of comes up in a technical construction, and it's a hypersurface that contains the logarithmic discriminant, and it has degree 2d times n minus 2 choose d, and full Newton polytope. And the way you get it is you take the reciprocal linear space, take its Howitz form, and sort of pull back the Howitz form to the coefficient space along the linear space that we intersected with. And so they are contained in each other, they coincide as sets, and hence the logarithmic discriminant almost equals this Hurwitz discriminant, we expect it to actually equal it, but we cannot prove this. So the worst case scenario is the power of the logarithmic discriminant, but we believe that the E is 1, but we currently have no idea on how to fill this gap in the proof. And this was the previously mentioned positivity result. If the arrangement is defined over the real numbers, so by real affine forms, then the logarithmic discriminant does not intersect the positive orthant, which you may think is trivial from Vashenko's theorem that tells us that the critical points are isolated in each of the bounded components, but there is an annoying technicality that allows us to not so quickly derive this. You have to go a bit into the weeds, and because the logarithmic discriminant is a closure of something, and so the boundary may introduce something in the positive orthant, you have to show that this does not happen. Though I personally believe that the fourth statement does not at all depend on the uniformity and should hold for all arrangements. Let me end by mentioning some sort of directions that are open and that I invite you to also consider if you like what we saw today. One particular arrangement, so Galen already asked for the other specific arrangements. One family that is very important also in the particle physics application is the arrangements whose complement is the moduli space M0, M of points in the projective line, modulo the SL2 action. How to get it? Well, we saw it already in the beginning, at least for the case of M05, is you take just the minors of this matrix. The two minors give you linear forms, and their zero set defines a hyperplane arrangement, which is actually up to some changing of variables and scaling, actually a graphical arrangement corresponding to the full complete graph. And in this case, it makes sense to index the variables by kind of which column they correspond to. So like ij is the minor corresponding to the ith and jth column. And so the logarithmic discriminant of this particular arrangement, M05, has degree 4. And it's actually quite manageable comparing to how annoying degree 4 polynomials in 5 variables can be. It's quite tame. And it's also of a very low degree. So if you look at the formula from the previous theorem and you plug into d equal to 2 and n equal to 5, you will find 12. So this has way smaller degree than the generic arrangement of 5 lines. And indeed, you see it's a very special arrangement of 5 lines. 2 of the lines are parallel, another 2 are parallel, and the fifth line goes through intersection points. And if you compare it to the Hurwitz discriminant, so the way we derived the result in the uniform case, the Hurwitz discriminant actually splits off extra factors. But also not enough to explain the 12. So, or the Hurwitz discriminant here has degree 8. And indeed, we looked into this and like for M06, M07, at least numerically, and observed some nice nested structure. So we computed some degrees, and we don't yet have a general formula, but we think that this really should have a nice structure that only waits to be uncovered. Into future research directions, you could look at nonlinear models, so arrangement of hypersurfaces instead of hyperplanes. If you only have one hypersurface and the rest are the variables, this is very much related to toric geometry and toric varieties. But we haven't explored this in depth yet. In the case of d equal to 1 is not so interesting, but can be covered using the work of our paper, just because a polynomial in one variable just factors into linear forms. So it's essentially, again, an arrangement of points on the line. But already for arrangements of quadrics in the plane, interesting things happen. For example, you could think of a quadric. So again, the two coordinate axes, and then one polynomial which depends on the parameter z. And for z non-zero, this is a smooth quadric. But for z equal to 0, this is a union of two lines. So this is a arrangement that degenerates to a hyperplane arrangement. And we currently only partially understand hyperplane arrangements, so we know that this special fiber has an arrangement of 4 lines, so the discriminant has degree 4. But if you take, instead of this, the discriminant of the family xz, and then let z go to 0, you get something of degree 6. Namely, you get an extra factor of u squared, u0 squared. And in this case, the discriminant is a factor of the takt invariant, because the likelihood equations are two quadrics, and we ask when they intersect non-transversally. So this is a takt invariant. And even for the linear case, there are a ton of open questions, but I'm just throwing on the last slide here. For example, how do we finish the kind of missing piece of the puzzle? Why is the Hurwitz discriminant reduced? Can we also just show that the projection is generically one-to-one? This we currently only know definitively in the d equal to 1 case. Is there an arrangement such that the logarithmic discriminant is not reduced, which essentially asks whether the ramification locus, this h tilde point I made from the beginning, whether this could have a repeated factor? I haven't seen this, but maybe there is something. Can this plane arrangement where the discriminant was split, I wonder, is this somehow minimal? Can you find a smaller arrangement that splits? Can you arrangement of lines maybe that splits? And maybe the most important combinatoric question is the degree of the logarithmic discriminant and the variant of the matrix involved. And if yes, what is its value? This would be kind of the holy grail of, for me, of logarithmic discriminants of hyperplane arrangements. Another more recent direction looked at by Barbara Betty, Victoria Borovic, and Simon Thelen is they looked at the other intersection points of the reciprocal linear space with our one linear space. I mentioned that a subset of these corresponds to the critical points, but there's more. And I looked into this in some examples and they as well. And there seems to be quite an interesting multiplicity structure hiding there. So if you like specifically affine matrices and you find this interesting, let me know and I'm happy to talk more about this. But that's all from me. Thank you.
Thank you so much, Leonie. Are there any questions? I might have a quick question. So, could you say a bit more about criteria for smoothness? Maybe even just in the case of the arrangements of points on a line. So when is the logarithmic discriminant smooth? Do we know this?
So if we go back to the points on the line, we saw in the beginning that for 3 points in the line, the discriminant happened to be a smooth quadric. But then already for 4 points in the line, this is always a singular surface.
Okay.
But it's a very, very natural question to ask, hey, when is the discriminant singular? And usually one expects this to correspond to kind of higher degeneracy. So not only 2 points come together to form a double point, but maybe 3 points coming together, or 2 points coming together at different points at the same time. So a kind of coincidence where there's more degeneracy happening. But this is again speculation. So these certainly are singular points, but our particular discriminant may have more singular points. Yeah, good question. Yeah.
Great, thank you. Any other questions? If not, let's go ahead and thank Leonie one more time.
Yeah, thank you so much for having me.
Thank you.
Lots